Assalamu alaikum. In this video, we are going to solve quiz number 1 for principal methods and applications of nuclear tracks. It consists of total 6 questions, which in this lecture we are going to solve step by step. So let's start with the solution of these problems. So in problem number 1, the mass of charcoal sample is given, which is 5 grams. Okay, and the activity of carbon 14 is also given, which is 63 disintegration per minute. Okay, and the half-life is also mentioned for the case of carbon 14, and T1 by 2 is equals to half-life is 5730 years. What you have to calculate, you have to calculate how old is the charcoal sample is. Okay, so you find the age of the charcoal. To find the age of the charcoal, there is a formula: T equals to minus 1 by lambda ln of R by R naught, whereas you know that lambda equals to ln of 2 divided by T1 by 2. Putting the value of lambda, you get minus T1 by 2 divided by ln of 2 ln R by R naught. So for that, T1 by 2 is given, which is this ln of 2, which is constant, and the unknown variable is R by R naught. So first of all, you have to find R by R naught, whereas R by R naught is equals to Rm, which is the molar mass, and T1 by 2, which is the half-life, R naught divided by R naught ln of 2, M, which is the mass in gram, and A, which is the Avogadro's number. So putting the values, R, which is given 63, molar mass for carbon we know that it's 12, and the half-life we know that it's 5730, whereas the divided by R naught, which is the constant value, and the value of R naught is 1.3 into 10 raised to minus 12, ln of 2 as it is, mass in grams, which is given 5 here, and N is 6.022 into 10 raised to 23. Because your answer is in years per meter, so you have to convert this into seconds to cancel out the units, because R by R naught is unitless quantity. Okay, both have same units, so they cancels each other, so you will get no unit. So to conserve units, so you have to, because upside is in numerator is 1 year, so 1 year has 3.15 into 10 raised to 7 seconds divided by 1 minute. 1 minute has 60 seconds. So after multiplying, you will get the value of R by R naught, and that is equal to 0.83. Okay, so now putting the value of R naught here is ln of R by R naught, so just find ln of R by R naught, it's equals to 0.1764. now you have to put this value here, so minus T1 by 2, which is the half-life, 5730 divided by ln of 2, and ln of R by R naught value is this. After calculating, you will get your time, how old your charcoal sample is, 1458 years. Okay, so now move on towards our second problem. Our second problem says that the isotope 40 means potassium can decay either to calcium or either to argon. Okay, so potassium either decays to calcium, and potassium either decays to argon, and the half-life is also mentioned, 1.26 into 10 is 9 years, and the ratio of calcium to argon decay, and the ratio of calcium to argon from the decay of potassium is also given, which is 8.54. you have to find what you have to find is how old is the sample is. So again, you have to find the age of the sample, so again you have to use the same formula: T equals to minus 1 by lambda ln of R by R naught, where again R by R naught is now given here. R by R naught, the ratio is 8.54. you have to put here 8.54, minus T1 by 2 means the half-life is also given, 1.26 into 10 to the power 9 divided by ln of 2 multiply ln of 8.85. after substituting your calculations, you will get your answer of how old how age is the sample is, and T equals to 3.89 billion years. So this how much old your sample is. Okay, now move on towards our third problem. Our third problem says that an ion source emits 633 kilo electron volts gamma photon and 606 kilo electron volts internal conversion electron in the K shell. What you have to find is to find the binding energy of the electron in the K shell. So E photon is given, which is 633 kilo electron volts. E of electron is also given. For the case of interconversion is also given, 6.606 kilo electron volts. You have to find the binding energy. Binding energy is basically the subtraction of gamma photon minus the electron energy. Okay, so minus gamma energy of photon, which is 633, minus the energy of electron, which is 606. After substituting, after minus, you will get your answer binding energy, and that is equals to 27 kilo electron volts. Okay, now move on towards our fourth problem. In our fourth problem, it says that the Q value of alpha particle decay of polonium is 5.25 mega electron volts. So the Q value is given here. Okay, and the masses of polonium and helium atom is also given in AMU. The mass of polonium polonium is 239.05217 AMU, and the mass of helium in AMU is 4.002603 AMU. Okay, what you have to find is the mass of uranium atom in the AMU. Okay, so first of all, you know that this is the alpha decay, and you know that alpha decay DQ value is always equals to parent minus daughter. So definitely polonium atom decays into uranium atom, and plus the emission of an alpha particle, which is helium. So polonium atom decays to uranium atom plus emission of an alpha particle, which is helium. So the equation of Q value becomes mass of polonium minus mass of uranium minus mass of helium. So to get the Q value, because we have to find the mass of uranium, so move mass of uranium to this side and move this Q to the other side, so you will get this relation. So mass of polonium and mass of helium given in the problem in AMU, but the Q value is given in problem is mega electron volt. So first of all, you have to convert this Q value into AMU, then have to put in this formula. So to convert mega electron volts to AMU, you have to divide your expression by 931.502. So after dividing the Q value 5.25 divided by 931.502, you will get your Q value in AMU, and that is equals to 5.63 into 10 raised to minus 3 AMU. Okay, so now you have to easily put this Q value in this relation. Mass of polonium, which is this, mass of helium, which is this, mass of Q value, which is this in AMU, all these in AMU. So you can subtracting, you can easily get your mass of uranium in AMU, which is 235.0439 AMUs. Okay, so now move on towards our fifth problem. Our fifth problem says that what is the maximum possible positron energy in the decay of argon. Okay, so argon decays into chlorine 1735 plus emission of neutrino with emission of beta plus, because argon it's a positron decay. Okay, positron decay, in positron decay there is always an emission of beta plus decay and with an emission of neutrino, and the masses of argon and chlorine in AMUs is also given, and the mass of argon in AMU is 34.980, and the mass of chlorine in AMU is 34.968, minus the mass of electron and in AMU is also 0.00054 AMU, and the relation of Q value in the case of beta decay is this: Q equals to parent minus daughter minus 2 m naught c square. Okay, this is the Q value expression in case of positron decay, because this is problem for positron decay, that's why we have to use this Q value formula. Okay, so after minus the masses of AMU, this minus this minus this, you will get your Q mass in AMU Q value, it's equals to 0.01146 AMU, and because this is Q value, so definitely this is the energy. Okay, this is the actual energy, so the actual energy is 0.01146 AMUs. To convert this into mega electron volts, you have to multiply this value by 931.502. so after multiplying this by 931.502, you will get your answer of energy of Q value 10.6 mega electron volts. Okay, so this is basically the maximum possible positron energy in the decay of argon. Okay, so now move on towards our last problem of the quiz 1 of principal methods and applications of nuclear tracks, and it's in this problem what is saying that the radium emits 4.60 mega electron volt alpha particle. Now E alpha is given, means 4.60 mega electron volts. Your radium decays into radon plus emission of an helium atom. What you have to find is the mass. You have to find the Q value of the decay. Okay, so there is also mass of radon and mass of radium is given in AMU. Okay, mass of helium is also given. To find the Q value, if E alpha is given, there is a relation Q is equals to E alpha capital M plus M divided by capital M, whereas capital M is the mass of recoil plus small m is the mass of the helium atom. Okay, so mass of the recoil is 222, as you can see, plus small m is the mass of helium plus 4 divided by capital M, which is 222, and E alpha, which is already given, 4.60. Okay, so after dividing, you will get your answer of Q value is in 4.68 mega electron volts. Second thing is you have to find the recoil energy, and recoil energy you can know that the Q value is always the sum of E alpha plus E recoil. Okay, to conserve the energy. Okay, so we have to find E recoil, so E recoil becomes Q minus E alpha. Q is we already find 4.68 given, whereas E alpha is already given 4.60. After subtracting, you will get your answer of E recoil, that is equals to 0.08 mega electron volts. So that's all for today. We solved in this lecture quiz number 1 of principal matters and applications of nuclear tracks. That's all for the quiz 1. Okay, if you have further any question, you can leave the comments below. Till then, take care. Allah Hafiz.